This is the second lecture about the quantum theory of the atom. Now, last time we looked at the wave nature of light, and this time we're going to start by thinking about light as a particle also. Now, it turns out that a number of experiments and theory in the early 1900s, people were having trouble reconciling the wave nature of light with what they were observing. And a number of researchers, including Max Planck and Albert Einstein, said, you know, we can explain some of this by saying that light can also act as a particle and not just a wave. And so we get what we can do with that is something like this: is we have the amount of energy involved in a certain, say, particle of light or packet of light is equal to something called h times nu, which now nu is just like the nu from before, which is the frequency of light, and h is something new called Planck's constant. Planck's constant has a value of 6.63 times 10 to the minus 34 joules seconds. Joules times seconds. Okay. So you can see that you can calculate the energy of a certain particle of light that has a certain frequency. You multiply that by the frequency in seconds or hertz with Planck's constant, h, and you'd end up with energy units of joules. Okay, so with this, what we can do is we can calculate the energy involved in a particle of light, a packet of light, something called a photon. It's called a photon. Okay, so light has particle properties, and it's not that light sometimes behaves as a wave and sometimes behaves as a particle. A better way to think about it is that for a complete description, we need to have both particle and wave-like properties. Or we need to be able to describe it as sometimes as a particle, sometimes as a wave. And it's mainly for convenience for us to be able to figure these things, to be able to understand these things. All right. So let's look at some of the evidence there is for, or let's look at what quantum theory means and what quantum theory means for the atom, and what evidence there is for a particle nature of light. All right, so an experimental basis for quantum theory. And this is a section of your text where I actually do encourage you to read sections 7.1 to 7.3 or so. And that will really help you get a little bit more. I oftentimes don't tell you to read the text really carefully. But in this case, reading the text may actually help with some of this, because I'm going to go over it relatively quickly. But one of the pieces of evidence for the idea of quantized, or the particle nature of light, is something called the photoelectric effect. And this was postulated by Albert Einstein. This is actually what he won or was awarded the Nobel Prize for. And it goes like this. I'm going to pull up this image from your textbook to be able to understand it. And the photoelectric effect is like this. You have a vacuum tube, which is basically just a closed off tube with no air in it. You have electrodes, a positive and a negative electrode, and one of the electrodes has essentially a metal surface or a metal plate on it. And it turns out that if you shine light on a metal surface, the metal will emit electrons. The electron is released and is attracted to the positively charged wire. Okay, so we're shining light. The electrons are being ejected. And what's interesting about this is that it only occurs when a certain frequency of light, when this only occurs when the frequency exceeds some threshold value that's characteristic of the metal. And the idea is this. So like once again, you shine light on the surface, electrons are emitted, but electrons are only emitted when the frequency of the light exceeds a certain threshold value that's characteristic of the particular metal that's used. Okay. So the idea is that the energy of a single photon must be large enough to remove an electron from the attractive force of the metal. And if the energy of the photon is lower than a certain value, then the electron will not be ejected from the metal. Okay. All right, so that's one piece of evidence for sort of a particle nature of light, is the photoelectric effect. Another one is atomic spectra. Atomic spectra, singular. Okay, so we all are pretty familiar with the fact, and this is an image from your textbook, that if you shine sunlight through a prism, you can split the light into red, orange, green, blue, indigo, violet, and so on, right? But it turns out that when you, let's say that you pass white light, sunlight, through a prism, and the light is dispersed into a continuous spectrum. A continuous spectrum would be like this. Now, if you do a different experiment, and here's an example. What I'm going to do is draw essentially a tube, a glass tube, and what we'll do is we'll put hydrogen gas into the glass tube, and across these electrodes, and it's a sealed glass tube, we have a negative and a positive electrode, and we put a high voltage or a high potential across those leads. And what happens is this, is that if you apply the high voltage, you get lines of radiation, of specific radiation wavelengths. And it looks something like this. Here's an example. This is figure 7.2 from your text. If you do this experiment for hydrogen gas, what you see is not, after you pass the light through a prism, what you see is not a continuum of light, but discrete bands of light at very certain wavelengths. If you do this for different atoms, you get different lines. For example, if you do it for sodium, you get a very yellow line. And this is what sometimes people used to use, and sometimes still do, sodium lamps for streetlights. You get a yellow light that comes out of it. Okay, so these are called atomic spectra. And I'm going to get to how this works, or how the idea that quantum ideas can account for this spectrum in a second here. Okay, so to do that, we're going to think about something called the Bohr model of the atom. So this is named after Niels Bohr. And this model is about 100 years old. Okay, and the important parts of this is that it's a model for the hydrogen atom. Remember, our goal in this chapter is to be able to figure out where the electrons are in space around an atom, and what role do they play in bonding, chemical bonding, and so on. We'll get to that soon, so for right now, we're trying to answer where electrons are around an atom. We know they're not in the nucleus. We know they're someplace around the atom itself. Okay, so the Bohr atom has a model is a model for the hydrogen atom. It incorporated quantum ideas. quantum meaning packet or of energy, a specific amount of energy, like we might get with a single photon, is a single packet of energy. And the Bohr atom, wonderfully enough, accounted for these line spectra that you see. Okay, so the Bohr model accounted for these line spectra that we get when we do an experiment where we put gases of each of these things into a vacuum tube and pass a current through it. All right, so the Bohr model looks like this. There are several different postulates that work with the Bohr model of the atom. Number one is that there are energy levels. Okay, and the idea is something like this. You have the nucleus, and these energy levels are where electrons can exist. So we have, say for example, we might have a nucleus, and we say that, okay, well we have energy level n equals 1, and we could have an electron there in that space. We could have energy level n equals 2, and we might have an electron in those space. 3, energy level n, energy level n equals 4. We might have electrons in these different spaces. So what it says is this, is that an electron of the hydrogen atom moves about the nucleus in a circular orbit. And the electron can only exist in orbits of certain radii. Which correspond to specific energies. And the energies are described by this quantum number n. Okay, and we can calculate these energies. It looks like this. The energy is equal to the negative of something called the Rydberg constant divided by the quantum number squared. The Rydberg constant is an empirically derived constant. It looks like this, 2.179 times 10 to the minus 18 joules. Okay, so this model for the hydrogen atom, we have energy levels where electrons could be. Now, they don't have to be in there. Obviously, the hydrogen atom only has one electron. So we can only have an electron in one of these energy levels at a given time because there's only one electron. Okay, the electron can exist in these orbits of certain radii, and these certain radii correspond to certain energies, where a higher quantum number would mean a higher energy. Okay, remember, our Bohr's goal here is to say, where is that electron exactly? All right, now, so how does this relate to the line spectra that we see for different atoms? Let's see how that fits in. Okay. The second part of the postulate is that electrons transition between energy levels. Okay, and it says that an electron can change its energy. Let's say this. An electron can change its energy by going from one energy level to another. And the idea is that these lines that we see in a line spectra arise due to these transitions. So lines arise when an electron emits a photon, right? Going from a higher to a lower energy level. Okay, so for example, we have, so let's look at let's look at a diagram of these energy levels that we might think of, and this is figure 7.9 in your textbook. But the idea is this, is that an electron or an atom can go from a higher energy level to a lower energy level, and the energy difference is emitted by a photon. Energy is conserved. An electron could go from n equals 3, quantum number 3, to quantum number 1, and that amount of energy would be emitted by a photon. And an electron could go from energy level 6 to energy level 4, and this amount of energy would be emitted as a photon. Now, of course, we can calculate these energies, right? The differences between these. Oh, and now let me point out also, an electron can change energy level from a lower one to a higher one by absorbing a photon, but that photon would only be absorbed, the electron would only be able to go from here to here if that energy was at least that much. In other words, it was enough to make that happen, and that's sort of that would give rise to these lines, right? The lines that we're seeing, evidence for the lines are. So electrons can go from higher to lower, lower to higher. If they're going from a higher energy level to a lower one, a photon is emitted. If we're going from a lower energy level to a higher energy level, the atom would have to absorb a photon. Okay, one thing to keep in mind is this, very important. Lines that you see, these lines that we see here in the atomic spectra, the atomic spectral lines are not the energy levels. All right, this is very important. It's what's being shown by the lines, these lines of energy, are the transitions between the energy levels. Transitions between the energy levels. So an electron's transition between energy levels are shown by the lines. And there's a whole, this is another figure from your text, but many of these lines were studied for a number of years to be able to say, oh, okay, well, you can predict the differences between these, and they have names: the Balmer series, the Lyman series, the Paschen series, and so on. Okay, but to keep in mind that what we're seeing here when we see these lines, the series of lines that one might have, they're named after the people that described the spectral lines. We're seeing a transition of an electron from a higher energy levels to a lower energy level that emits a photon. Okay. Let's go back now and look at how we might calculate the energy of these things. And here's an example. So let's say we have an electron that's going from a higher energy level to a lower energy level. Some initial energy level is going to be given by the Rydberg constant over the initial quantum number. The final energy level would be given by the Rydberg constant over the final energy level. Okay. So how would we predict what the wavelength would be? How would we predict what the wavelength would be when we're going from energy level 2 to energy level 1, for example? Okay, so let's get a general equation to be able to do that. Okay, well, so we know that the initial energy level is going to be equal to the final energy level plus the energy of the photon that was emitted. So if a photon is emitted, its energy would be equal to the initial energy level minus the final energy level. Okay, substituting these things into here and rearranging, we can end up with the following. The energy, E equals h nu, remember, is equal to the Rydberg constant. So I've rearranged a little bit, done a little bit of algebra just to speed things along. Times 1 over the final energy level squared minus 1 over the initial energy level squared. Oftentimes you might be interested in the frequency of the light rather than the wavelength of the light rather than the frequency. And remember, the speed of light is equal to lambda nu, right? Where this is the wavelength, this is the frequency. We can combine these. And if you're interested in the frequency, the equation would look like this. Hc times 1 over the final energy level minus the initial energy level. So with these equations, you can calculate the energy that would be given off if an electron is going from, say, energy level 3 to energy level 1. So the initial would be number 3, so we'd have an energy level 1. The other thing you can do is you can calculate, for example, if you know the wavelength of light and you know an initial energy level, you could find the final energy level. And there are several homework questions that deal with this. Most of this is relatively straightforward. Take your time and do the algebra correctly. Take your time and do the algebra correctly. That will seriously help you out. Okay. Let's think about the importance of the Bohr model. Okay, so we have the quantization of energy levels. We have this is really the basis for the modern picture of the atom. But there are problems with it too. So the limits of the Bohr model are the following. There's no fine structure of the hydrogen spectrum. So for example, if we were to look at these lines very, very closely with a very good prism, essentially, we would see that there's actually, in many cases, multiple lines that are there, not just single lines. So that's one of the problems with the Bohr model. How do we account for that if we simply have these energy levels? There's no explanation for systems with more than 1 electron. Okay, so this picture works great if you're talking about hydrogen. So this picture works great if you're talking about hydrogen. The picture works great if you're talking about helium, but you removed 1 electron, so there's only 1 electron. It works great for lithium, and so on. Okay, and what we're going to see next is how we can use quantum mechanics, or how quantum mechanics was developed, to be able to be able to sort of incorporate these ideas where the Bohr model works well, but also take into account and create a picture of the atom that takes into account these other things here. Okay, so we will see that in the next video.